Magandang araw mga kapwa DOST scholars. My talk this morning is about a topic that we usually forget as scientists. But in reality, our practices in science, such as implementing peer review, are affected by this. This is the philosophy of science. Let's go back to the ancient times when the institutions of the academia are being formalized. That time, knowledge, which is now considered as part of science, is heavily based on deduction. The dominant system to investigate social, life, and the physical world is through an organized system set by the scholars. One of the philosophers that time is Aristotle. As you know, in deduction, we cannot go outside the set system, and we need to establish new knowledge by working inside that set system. For example, in mathematics, we use the axiomatic system, which is anchored on deduction. In an axiomatic system, we have the axioms, which are building blocks of our system, like the DNA that can give birth to an organism. The set of axioms is the general framework where we can deduce specific new knowledge known as theorems. The new knowledge or theorems are not outside the system, as they are quote unquote discovered by using only the set of axioms. The set of axioms is the mother of all theorems within that system. For example, let us have these four axioms. Every hive is a collection of bees. Any two distinct hives have one and only one bee in common. Every bee belongs to two and only two hives. There are exactly four hives. Whether these axioms are true or not in reality, we assume the axioms are true within the system. Do you know that by considering these four axioms, we can have new statements as follows? There are exactly 6 bees. There are exactly 3 bees in each hive. For each bee, there is exactly one other bee not in the same hive with it. We deduce these new theorems by just using the four axioms. We don't need other information, just the axioms. The practice of deducing the theorem from the axioms is called proving. A well-known theory in mathematics is the Euclidean geometry that we have learned in our high school geometry class. We have many theorems there if you remember your high school. Did you know that those theorems in high school are based only on 5 axioms or postulates? They are shown in the screen, the Euclid's postulate. Axiom 1 or the ruler postulate. Given any 2 points, you can draw a straight line between them. Axiom 2, any line segment can be extended indefinitely. Axiom 3 or the compass postulate. A circle may be drawn with any given radius and an arbitrary center. Axiom 4, all right angles are equal to each other. And the last postulate, through a given point, only one line can be drawn parallel to a given line. These 5 axioms created the whole Euclidean geometry. Imagine that. The 5th postulate, commonly known as the parallel postulate, became famous because some mathematicians modified this 5th postulate. And you know, because of that modification, they go beyond that set axiomatic system. It gave rise to new mathematics known as non-Euclidean geometries. In an axiomatic system, if you want to create new theories, you need to go beyond the set axioms, especially if what you are proposing is inconsistent with at least one of the original axioms. These statements outside the original axiomatic system can give rise to revolutionary knowledge. However, it is not that easy. Mathematicians back then tried to find a universal axiomatic system that can encapsulate all knowledge. But Kurt Gödel showed that this is not possible. Indeed, the incompleteness theorem by Gödel killed the dreams of many mathematicians to have a universal axiomatic system. In layman's language, the implication of this theorem is that a complete and consistent list of axioms can never be formulated. Each time an additional consistent statement is added as an axiom, there are other true statements that still cannot be proven. On the other hand, if an axiom is added that makes the system complete, it does so at the cost of making the system inconsistent. While this is a negative news to some mathematicians, these provided an opportunity for us to create new theories and to expand the body of knowledge. Going back to Aristotle, deduction was the dominant way of formal thinking back then, even until the Dark Ages. However, as you know, growth in knowledge, while possible, is too difficult as we need to work outside the established axiomatic system, and we may have a war among our colleagues. During the Renaissance, Francis Bacon advocated induction, which we know is in contrast to the ways of deduction. When a hypothesis survives a test, then it is confirmed. So we do test to confirm, another test to confirm, test, confirm. This induction or confirmation helped to think outside the box and pushed science to flourish. This helped in the innovations during the Industrial Revolution. New theories sprout like mushrooms. This is why during the time when induction became the dominant way of thinking, they called induction as the glory of science. However, it is a scandal of philosophy. Why? Because of the black swan phenomenon. We cannot generalize. For example, suppose we are in a lake, then we saw a white swan, then we saw another white swan, then another white swan. Can we generalize that all swans are white? What if there's a black swan? In deduction, results are surely true within the system. But for induction, we cannot generalize and say that a statement is true for all cases, even within the system. So after 500 years, a new way of thinking was proposed by Karl Popper, the process of falsification. Popper's way of thinking is one of my favorites. Similar with induction, theories need to be tested. However, unlike induction, which is about confirmation, falsification is about testing a theory to falsify it, not to confirm it. Continuous testing is done, and the theory that survives the test becomes stronger and stronger. But surviving the test does not mean it is true. There is no absolute truth. This is similar with mathematics, where we look for counterexamples to disprove a statement. Hence, as you see, falsification is deductive in nature. Falsification is combining both induction and deduction. Falsification is also used as a demarcation of science from non-science. Statements that cannot be tested is non-science, such as topics in religion. Although, just a note, in the Wissenschaft practice, it is not healthy to put boundaries between hard sciences, soft sciences, arts, and the humanities, especially when we are talking about generating knowledge towards human flourishing. As an application, we know that in statistics, many people misuse statistical results. Conclusions tested using statistical methods are not the absolute truths. Statistical results, given the evidence, only mean that results are worthy of further investigation. Though they can be useful in many ways, but they are not absolute truths. One of my favorite examples is the mathematical model of general relativity of Einstein, published in 1915. Einstein's field equations describe gravity as a result of space-time being curved by mass and energy. This became popular as it replaces Newton's theory as the dominant theory to describe gravity. Newtonian physics does not predict with accuracy the orbit of Mercury, but Einstein's theory of relativity does. In 1919, the team of Arthur Eddington tested Einstein's theory, and Einstein's theory passed this experimental test. During the total solar eclipse in 1919, it was explored whether the immense gravity of the sun will bend the incoming light from more distant stars, as predicted by Einstein's theory. Though not really for general relativity, but this is for special relativity, a test was done by Haefele and Keating of the U.S. Naval Observatory to test time dilation. They brought atomic clocks aboard commercial airliners and went around the world, one going west and one going east. They observed that the east-going clock lost some nanoseconds, while the west-going gained several nanoseconds compared to the similar clocks that stayed in Washington. As we see, for many years, many scientists tried testing Einstein's theories, and the theories survive. Just recently, in 2016, if you remember the news, a very, very nice scientific news that time, in 2016, gravitational waves generated by two colliding black holes were first detected and observed on Earth, as reported by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Also, another amazing news, very recent, in 2019, the first image of a black hole was published, following, of course, Einstein's prediction. This was a huge achievement for science. However, the testing continues, and several scientists are checking if Einstein's theory can survive even inside a black hole. And also, we know that Einstein's theory of relativity passed every test, but they are incompatible with quantum theory, which also passed every experimental test. So as you see, this is how falsification works. Moving forward, after Popper, a physicist and philosopher, Thomas Kuhn, proposed the concept of paradigm shift during scientific revolution. Here, Kuhn explained that science is historical, that there were series of normal science, then crisis, then scientific revolution, then normal science again. Unlike Popper, those theories that succeeded several tests but then failed need not be fully abandoned. we can consider them as part of one, perhaps possibly older paradigm. For example, Newton's law of universal gravitation can still be taught in high school subjects, as this is simpler and while less accurate for very large masses and speeds, yet it can still give sufficient results for most applications on Earth. For many disciplines, I know you can give examples. We know there are many examples of scientific revolutions. Am I right? But of course, since I work on modeling the dynamics in evolutionary biology, I will present the theory of evolution as one of the amazing examples. We know how this theory revolutionized and shaped how we think of biology today. If we softly extend that theory of evolution to our topic we are discussing today, we see that scientific theories and the scientific community also evolve. I now want to address the PhD students here in our Zoom conference. The ASEAN and Philippines qualifications framework for outcomes-based education highlights that level 7 is for master's program and level 8 is for the PhD program. Level 7 says that a graduate of a master's degree is expected to be at the forefront of a field, really advanced. But what that student may be studying is still inside the area, the discipline. A PhD graduate is expected, as shown in level 8, a PhD graduate is expected to be at the frontier of a field. If you reflect on this, PhD studies should be at the frontier of a field, at the edge of a discipline, to break walls, to break barriers, to shake philosophies. We are expected to go beyond our areas to create new theories, new knowledge, skills, and frameworks. However, when we create new theories, we should remember to consider many areas around us. For example, in mathematics, we have the theoretical maths, the applied maths, and the application areas. It is also important to note that maths and science education play a big role in developing experts. There's also the maths and science communication and diplomacy, so we can have significant impact to our society. And our practices should be anchored on strong ethical framework. To end, I summarize my points. First, science is dynamic and we can continuously innovate and grow as human beings. Second, think outside the box. Be at the frontier of a field. Third, testing is part of our job as a scientist. This may also mean that what we do in testing will contribute to the body of knowledge. We are part of a bigger picture, of a bigger community. And lastly, teach not just the what and how, but also the when, the history, and why, the philosophy, and facilitate innovation and foresight. Again, this is Jomar Rabajante from UPLB. Maraming salamat sa panonood. Thank you.